Hi, I'm going to be looking at standing waves in some detail in this video. I'll be looking at how standing waves are formed, the features of standing waves, and some rules for how harmonics form, and then I'll look at the harmonic patterns for strings, open pipes and closed pipes. So let's get started by considering what you need to form standing waves. You need two identical waves that are moving in opposite directions. Now, by identical waves, we mean they need to be of the same type, okay. Now, if they're the same type, that means if I want to form a standing wave on a string, then I need two progressive waves that are waves on strings. Or I need two microwaves or two sound waves. I need two waves of the same type. And they need to have the same frequency. If they have the same frequency, they have the same wavelength, that follows. And they need to have the same amplitude as well. So that's what I mean by two identical waves. They are progressive waves. And they need to be moving in opposite directions. And I need those waves to pass through each other so that they can superpose. So here are my two waves here. I've got a dotted line here and a blue line here. Wave 1, wave 2. They're moving in opposite directions. They have the same amplitude and same frequency. They're going to pass through each other and they're going to superpose. And those are the ingredients for a standing wave. And as they pass through each other, they superpose, we get a resultant wave. The standing wave is the resultant wave, and that's what we actually see. So these are two progressive waves, but the standing wave is the resultant of the superposition. That's what we actually see. So now let's look at that. Here are my two waves at time 0. So we call this t equals 0. They are meeting in phase at this instant in time. In phase. That means we get constructive interference and they form a double amplitude wave. So we get something like this. I'm afraid my wave drawing is a little bit out today. It's always worth practicing your wave drawing. I mean, yeah, it's a bit difficult on a whiteboard, but I can usually do better than this. So it's not very good, but hopefully you get the point. So the solid black line is a resultant wave, and that's what you would actually see, a double amplitude wave at t equals 0. So that's what we'd see. And then a little bit later, they're going to, because they are moving and we get that changing phase relationship. I should write that down actually. We get a changing phase relationship. That's the key thing here. And they're going to go out of phase and into antiphase like this. So here are my waves and we're getting a peak meeting a trough meeting a peak. So the waves are in antiphase. They're going to cancel each other out. Destructive interference, cancel each other out. So the solid black line is what we would see at that instant in time. This actually occurs at a quarter of the cycle later. So if you imagine you could freeze one wave in space and time, which would not make sense because it's a progressive wave, but just imagine you could, and then the other wave is moving relative to that, you'd expect this to happen half a cycle later because it's going to take half a cycle for that trough to move there and half a cycle for it to move there, or from here to there. It would take half a cycle. However, because they're both moving in opposite directions, the relative speed is doubled, so this happens a quarter of a cycle later. They meet in antiphase. So we need to write that down. Antiphase. And then another quarter of a cycle, they'll be back in phase, but the other way around. So where you had a peak form, you now have a trough form, and vice versa. So we should get something like this. There we go. So this is T half a cycle. Half a cycle later, they are back in phase. Give us that double amplitude wave, except now it's the inverse of what we had before. And that's how standing waves move. They oscillate up and down like this. Whereas with a progressive wave, you see the peaks moving left or right, if you're looking at from the side. Here, those peaks and troughs just go up and down. So what this standing wave has done has trapped the energy. Progressive waves transfer energy from one place to another, but standing waves trap it. And they trap it in these bits here where we're getting this maximum displacement. So let's look at the features of the standing wave then. At this point, or let's look at this point here. This point here, that is at zero displacement. That point there is, I think that should be around here. Yeah. That is still zero displacement. And it's here now. And that is zero displacement. So that same point, I think I've got that one right anyway. That same point in each of those scenarios is always zero displacement on the resultant wave. And those points on a standing wave are called nodes. So that's a node. And all the points where you always have zero displacement, we call those nodes. So we've got some features of a standing wave here. Nodes. That's always zero displacement. That's a key feature of a standing wave. You can see them here, 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 and here, 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 here. You can't really see it here because it's zero all the way along. And then you get these points where you get the peaks and the troughs forming, and those are they're quite the opposite of where you have zero displacement. You always have maximum displacement there. And they are called antinodes. Maximum displacement at the antinodes. So those are the two key features of the standing wave. You can see that it's still forming a wave of the same wavelength as the progressive waves that formed it, and the wavelength can be measured according to can be measured from the nodes and the antinodes. So if you see we're going from, this is an antinode here, this is an antinode there, and we've got another antinode there. This is a node, okay? You can see that if you go from one antinode to the next, you're going from a peak to a trough. So that is half a wavelength, and you're going from a trough to a peak, that's half a wavelength. So an adjacent antinode to an antinode, it's adjacent, I should say, that's half a wavelength. And the same is true of going from a node to a node. So here you're between a peak and a trough, and here you're between a trough and a peak. So those 2 points are half a wavelength apart as well. So the distance between adjacent nodes or adjacent antinodes is half a wavelength. Nodes and antinodes are evenly distributed around, so they're all half a wavelength. If you're actually doing an experiment with this, then you might, if you wanted to measure the wavelength, you might measure several sets of antinodes or nodes, depending on what you're measuring, to make sure that you can average as well. Okay, so we've seen what's happening. And, of course, in being in phase and antiphase, those are the extremes. So at some time it's in phase, and then it will gradually go out of phase to antiphase, and then gradually from antiphase into phase. So you get lots of different positions in between these, but these are the key points that we're interested in, so we can understand what's happening with the standing wave. Now, standing waves form at specific frequencies. So we've got for a given situation, and we'll look at some experimental setups in the video, or I'll mention them. If you had a situation with a string, then the standing waves on that string will form at specific frequencies. They don't form at just any frequency. You get the first standing wave form. The specific frequencies are called harmonics. So that is a key word that you should know and be able to use. Harmonics are the specific frequencies at which standing waves occur. And the first one is called the fundamental mode of vibration. That occurs at a frequency which we call F0. So that's the fundamental frequency. And you can see that by calling these harmonics, what we're talking about here is the physics of music. Music uses harmonics, which are due to standing waves forming on the instrument you're talking about. Might be the string in the piano, string on the guitar, the sound in an air chamber of the instrument. But either way, it's the physics of music. Okay, now the first harmonic occurs at F0. Any subsequent harmonics will occur at a multiple of F0. Let's see if I can actually write subsequent harmonics. So if we call that NF0, some number, it'll be an integer multiplied by F0, but not necessarily going up. One after the other. Might not be 1, 2, 3, 4 in each case. In a lot of cases it is, but you need to look at what you're forming the standing waves on, which we will look at. So that will come up. Yeah, subsequent harmonics occur at a multiple of F0. So we've looked at how you form standing waves. You need two identical waves that are moving in opposite directions. You need them to meet and superpose. And then we've looked at why the standing wave forms because of this changing phase relationship. And we've identified what nodes are. They are places of permanent zero displacement. Antinodes are places where you always have maximum displacement. Then we've seen that you can work out the wavelength from measuring the distance between adjacent nodes or antinodes. And then standing waves occur at specific frequencies which are called harmonics. And the first one is F0. Every other harmonic is some multiple of F0. So now I'll clear the board and then we'll look at some rules for identifying how to work out the pattern for certain standing waves and then look at the harmonics for strings and different types of pipe. Right, up here is the summary of what we've seen so far. You need your two identical waves travelling in opposite directions. The fundamental occurs at F0 and subsequent harmonics occur at a multiple of F0. Here are some rules then for when we get harmonics forming. Firstly, strings. They always have a node at each end. Okay, so that's our rule for if we've got a string and we move one end of the string up and down, causing a wave to propagate across and be reflected, then if you have a harmonic, you always have nodes at either end. Pipes. Now pipes, when we're making sound waves in pipes, we're using sound. So sound is travelling down the pipe and being reflected at the other end, giving us our two waves. And the sound can form a standing wave in there. Now pipes can either have an open end or a closed end. So there are two parts to this. If you've got an open end, you have an antinode form there. And if you have a closed end, you have a node form there. These are vibrational nodes and antinodes, which are different to pressure nodes and antinodes, which you may, if you're looking in textbooks, you may see them spoken of. So at the closed end, you can imagine the closed end is constraining any parallel vibrations, because remember sound is longitudinal, so the vibrations occur parallel to the direction of travel of the wave. So it's constraining them, meaning you get a node form there if you have a standing wave. And at the open end, you have the opposite happen, so it's not constrained, I guess you could say, and therefore you get maximum vibration there. But anyway, those are the rules for strings and then for pipes. Now, nodes and antinodes always alternate. You can't have two nodes together or two antinodes together. So these must alternate if you have a standing wave. So that's my third rule. And the second rule is that the fundamental occurs with the fewest number of nodes and antinodes given these rules above. That's right, this is nodes and antinodes. So that's rule 4. Rule 5 is the next harmonic occurs by adding on one node and one antinode. So you get plus one node, plus one antinode. So those are my rules for when you get the harmonics formed. Now let's look at specifics. We'll look at some harmonics in strings, followed by some harmonics in open pipes and then closed pipes. And we'll see how these rules help us to figure it out. So we'll start with strings. With our setup here, we have vibration generator, string, pulley, and a load. That vibration generator would be connected to a signal generator to give you a constant frequency input to this. So this end's going to go up and down, cause a wave to propagate along the string, and it'll be reflected at the pulley. Now that's the thing, to get us our two identical waves, the easiest way to do that, by far, is to have a wave reflected so that you get your identical wave in the reflected wave. So that gives you an incident and a reflected moving past each other, so you can form your standing wave. Okay, so wave 1 goes down there, that's the incident, and then you have your reflected as well. That's the setup. Now let's look at the harmonics. So first, if I just draw a dotted line there. If we look at our rules for strings, if we're going to have a standing wave at all, we need a node at either end. That's one there, one there. So we're going to put this on there. Node, node. Now, the nodes and antinodes must alternate. So we need at least one antinode in the middle here, otherwise they wouldn't alternate. Now that gives us the fewest number of nodes and antinodes possible. We don't need any other nodes or antinodes to give us an alternating pattern here. So that would be our fundamental. So this is carrying at F0, this is the fundamental. Okay, so what would the actual shape of the wave look like? Remember, at the antinode you get maximum vibration, so you get a peak or a trough form there, and at the nodes there's no vibration at all, so we can draw that like this. That's showing at some point it's a peak, and then at the other extreme it forms a trough. So we've got our fundamental there, that's the fundamental for a string. If we were then to, and the way that we would actually form that in practice is we take our signal generator, we keep increasing the frequency from 0 up until we get this formed, and that's our fundamental. Okay, now let's look at the second harmonic. So this is the first, second harmonic would be like this. Oh, and yes, course, we can do some analysis here. So we know the frequency at which this is occurring from our signal generator, and we can work out the wavelength by measuring this length here. So this is L, and you can see the distance between two nodes is half wavelength, so that's equal to lambda over 2. The wavelength there is 2 times L. That L is half a wavelength, so to work out the full wavelength we need to multiply that by 2. Okay, so that's the fundamental. Now let's go to the second harmonic. So we keep increasing the frequency on our signal generator. And what would we get formed here? Well, it's still on a string, so we've got our 2 nodes from rule 1 there. We're going from the harmonic, we're going up to the next harmonic. So we go from the first harmonic, we go up to the second harmonic. So we need +1 node and +1 antinode. Now here we had 2 nodes, so we need 3 nodes. They're going to be evenly distributed. So that one's going to occur right in the middle, right between those 2. And we need 2 antinodes, and they're going to occur in between to give us that alternating pattern. So now we've got 3 nodes, 2 antinodes. So we had 2 here, and 1, 3, and 2. Okay. So what would this look like? At the antinodes, we get the peaks and troughs formed. So this one might be a peak here, that one a trough, giving me that shape. Okay, so we've got nodes and antinodes, and they're sketched out. That's what a wave would look like. And this peak would go down to form the trough, and this trough will go up to form the peak, and so on. So it'd oscillate like that. Right, now what frequency does this occur? We know it occurs at some multiple of f0, we've already said that. But what multiple does it occur at? Well, let's take a look at the length. Okay, now this L here, the length of the string, is taking us across this node to node, and this node to node. Now, each of those is half a wavelength, so that means that we've got a half plus a half gives us the full wavelength. So L is equal to lambda, or lambda equals L. How has that changed from last time? So we had 2L here, this is 2L, now it's L. So the wavelength has halved. You can see that, the whole wave is filling in there, whereas we had half before. So that means if the wavelength is halved, then the frequency must have doubled. And if you check that on an experiment, you'll see that indeed that is true. So that's the second harmonic. Let's put that was in brackets there. What about the third harmonic? So it's a signal generator there. Putting. Okay. We had 3 nodes and 2 antinodes. Well, we need to have +1 of each of those. So we're going to have 4 nodes and 2 antinodes. We know 2 of the nodes must form at the ends, because that's what rule 1 says. So now we need to evenly distribute our nodes across there, as like so. And then the antinodes go in between them. So we've got an antinode there, antinode there, antinode there. And that would be the pattern for the third harmonic, and then we just draw the shape of it. So we've got a peak, go to a trough, go to a peak again. That's not a very good trough, I do apologise. And then I can show at the other extreme it would look like this. That's our third harmonic. So we've got 4 nodes, 3 antinodes. And what frequency does this occur at? Well, the length now is equal to a half plus a half plus a half. that's 3/2, so 3/02 lambda. Okay, what does that mean? Lambda is equal to, it means it's 2/3 of L. We had 2L to begin with, so we've divided that by 3. That means that the frequency we'd expect that to occur at is 3F0. Right there. 3F0 is when the third harmonic occurs. Those are the first 3 harmonics of the strings, and that would carry on in much the same way as we've done it here, so I won't go any further than that. Those are sounding waves for strings, those are the harmonics. I'll now draw the harmonics for open pipes so we can see what happens there. Before I go on to open pipes, actually, let's notice this, which might be a helpful way to figure out the pattern for a given harmonic, which is that at the first harmonic we had one antinode and 2 notes, but there's one antinode. At the second we had 2 antinodes. Third we had 3. So if you wanted to draw the 5th harmonic, you'd know that there would be 5 antinodes. And then we always had one more node than antinode, and because they just go up by 1 each time, that would always be true. So at the 5th harmonic, we would know there'd be 6 nodes. And you know, for strings, because you've got this rule already, you'd have a node at either end. So you could work it out quickly from there, a very high harmonic, which would actually be very hard to produce in real life. But nonetheless, you could perhaps use that as a way of figuring something out. So hopefully that would be of use. And we'll do that for the other types of standing wave as well. Right, let's clear this. Let's look at open pipes now. What do we mean by open pipes? An open pipe has both ends open. So that's a cross-section of my pipe. And in order to produce a standing wave in there, I play some sound down the pipe from one end. And to do that, I'll use a loudspeaker, which is connected to a signal generator to give me that constant frequency sound going down that end. So the speaker is there, and the diaphragm of the speaker vibrates. That actually is an antinode, as an open end there. And the wave will reflect here. It'll actually partially reflect and refract at the open end due to a change in acoustic impedance there. So we get some go off there, and some gets reflected. So that gives us our 2 waves, our incident and reflected. Right, now let's look at the harmonics. So we have the cross-section of the pipe here. When does the fundamental occur? Well, let's look at the rules. We're dealing with 2 open ends here. So if we can have a standing wave at all, we must always have antinodes here and here. That's for all of them, and we need to have the fewest number of nodes and antinodes that will alternate. Well, just like the strings, we just need to add one more there, which in this case is a node, whereas with the strings it's an antinode, and that gives us an alternating pattern with the fewest number of nodes and antinodes that satisfy these rules. So that is the fundamental for an open pipe. This occurs at F0. And now, and one thing I should say about F0 actually is that if you have one string set up, then that occurs at a particular F0. But if I set up a longer string and a heavier string, that will have a different fundamental frequency to the other string. So each setup has its own fundamental frequency. Now, just as before, we also increase the frequency from 0 up until we get our standing wave form. Now, this is an antinode, so we're going to get a peak form here, and it'll be at 0 here. I'm going to use transverse representations of the wave, even though it's longitudinal. The transverse will just help us to visualize it much better. So we get a peak, goes to 0 here. Now you know that adjacent antinodes, if one's at a peak, the other one is at a trough, they're in antiphase with each other. So it's going to go down like this to the trough like that. So that would be our wave, and it would oscillate like this. So that the other extreme would be like that. How much of the wave do we have formed here? Well, node to node is half wavelength, and so is antinode to antinode. So the length of the pipe would be equal to half of the wavelength. So we've just got half a wavelength in there. And you're going to see that the open pipes are very similar to the waves on the strings. It's just where we had nodes on the strings, we've now got antinodes and vice versa. So we get a different pattern forming. That's our wave here, and the wavelength is equal to 2 times L. We've got 2 antinodes and 1 node. So that's the first harmonic, the fundamental. Now let's look at the second. In order to satisfy the rules, we need 2 antinodes, one at either end. But we're going up to the next harmonic, so we have plus 1 node and plus 1 antinode. To make sure my antinodes are evenly distributed, that one must go right in the middle. And then the nodes go in between these to give me alternating nodes and antinodes. So if I say this is a peak again, it's down to 0, 0. This will be at a trough, this will be at a peak. So I'll get something like this formed. And at the other extreme, it'll be like this. So how much, what frequency would this occur at? Let's first work out the wavelength. This time L is equal to half here, that's antinode to antinode, and half here, so that's equal to lambda. Lambda equals L. The wavelength is halved, so this would occur at 2f0, and indeed if you do this experiment you'll see that it does. We can also write that we have 3 antinodes and 2 nodes. That's the second harmonic. Third harmonic then. Antinode, antinode. You could also guess, just like I said with the strings, we've got 1 node here, we've got 2 here, we're expecting to see 3 and 4, so third harmonic, 3 nodes, or second harmonic, 2 nodes, sixth harmonic, 6 nodes. That's how it'd be with open pipes. So we can have 4 antinodes and 3 nodes. So I've got to evenly distribute my antinodes across here, like that, and just fill in the gaps with the nodes. And if this is at peak, this will be at trough, that'll be at peak, that'll be at trough. Trying to go through 0 at that point as well. We can draw that. Always worth getting practice in drawing waves. Okay, the other extreme would be like this. There we go. The wavelength then, that'd be a half, plus a half, plus a half, 3 halves. 3 halves of lambda. So lambda is 2/3 of L. Just like with the strings, that's a third of the fundamental wavelength, so frequency is tripled. 3f0 for that harmonic. And that's the third harmonic. So we can see, like I was just saying, first we have 1 node, second 2 nodes, third 3 nodes. So if you wanted a quick way to work out how many nodes and antinodes you've got at the fifth, you'd know there'd be 5 nodes and 6 antinodes. So you could use that to plot out quickly what that harmonic would look like. So those are harmonics for open pipes. Next is closed pipes, so let's clear the board for those. Closed pipes. Closed pipes have one end that is closed, the other end is open. So the experimental setup here would be, here's my speaker connected to the signal generated like before. That's an open end, and then this end is closed. So the wave will reflect off the closed end here. That's how I could set it up here. So we get incoming. Now this one does not follow the same trend as we've seen with the strings and open pipes. So this one is more prone to catch people out, I suppose you could say. Let's have a look at what happens. So we've said that if I have an open end, I'll have an antinode form there, and if I have a closed end, a node will form there. And then for the fundamental, I need to have the fewest number of nodes and antinodes that satisfy that and the alternating rule for nodes and antinodes. So I know I'm going to have an antinode here and a node there. Open end, closed end. So do I need any more nodes and antinodes to satisfy these rules? Well, no, I don't. This is already alternating, and I've got one at the closed, a node at the closed, and an antinode at the open end. So this is the fundamental. That's what occurs at F0. So if we use the transverse representations again, even though this is actually sound, it's going to be at 0 here, and it's going to form a peak or a trough here. So if I draw a peak there and then have a dotted line, oh, that's not very good. It would help if my pipe was a little straighter, which that wasn't. Okay, yeah, that's not too bad. Right, so we get our peaks and troughs forming at the open end there. How much of the wavelength is present here? So the length of the pipe this time. Well, if a node to the next node is half a wavelength, then we're not even going that far. We're actually going, and an antinode is halfway between nodes, so that means this must be a quarter of a wavelength. So, quarter of a wavelength is present here. That means that lambda is 4 times the length of that pipe. That's our fundamental for a closed pipe. Something about drawing that bottom one. It's not going well today. There we go. Now let's see what happens at the second harmonic. In order to satisfy the rules, we know we need to have an additional node and antinode, and they must alternate. So, oh yeah, here we had one node, one antinode. Well, if we're going to have one more of each, then we're going to have 2 nodes and 2 antinodes. And we just need to make sure they alternate along here. We've got an open end, closed end. So my node will form about there and the antinode there. And that would be the plot for, or the pattern for the second harmonic. It's going to be at 0 here. I can have a peak forming here if we want a peak. That's going to be a trough there then. So this shape will be like this. Oops, went up a bit too fast there. There we go. And the other extreme, that's the second harmonic. How much of the wavelength have we got? Well, we have half here, because we're node to node, and then we're node to antinode again, and that we know is a quarter. So we've got a half and a quarter. So this time the length is 3/4 of the wavelength. That means the wavelength is equal to 4/3 of L. And it's for that reason that the frequency at which this occurs is 3f0. It's not 2f0 like before. With a closed pipe, you won't get a standing wave form at 2f0. It's not possible because you can't have the an additional set of nodes and antinodes until you get here. So that's the second harmonic, and this is, now you can see it's following a different trend. Okay, but you can see that you've got equal nodes and antinodes. So first harmonic, you've got one of each. Second harmonic, you've got two of each. Let's draw the third. Third harmonic. We're going to have three of each now. Got to make sure we have node at the closed end, antinode there. Now, three of each, eh? So, one there, one there, one there. That's three of each, yeah. Now we can sketch out our pattern. We can keep the peak there if we want. Peak, trough, the peak again. It's not very well even, not very evenly distributed. Just going to shift that on a bit. Okay. Right, let's sketch that. Right, not the best sketch in the world, but get the idea. That's better. Okay, so how much of the wavelength do we have here? L is equal to a half plus a half plus a quarter. Half, half, quarter, that's 5 over 4 lambda, or it's 1 and a quarter. So that means that lambda is 4L over 5. So the wavelength is 5 times smaller than the fundamental, meaning that the frequency must be 5 times higher. And indeed, if you do this experiment, you will see that that is what would happen. So that's the first three harmonics for a closed pipe. And here you can just see, if you're at the fifth harmonic, you need 5 nodes and 5 antinodes. Node at the closed end, antinode at the open end, and then just evenly distribute them along the length of the pipe. Right, so we've seen harmonics for strings, for open pipes and closed pipes. Yeah. Now, just on to some additional notes, so I'll just clear the board so we can do that. Okay, a couple of notes about sounding waves. First one, this is to do with using closed pipes to determine the speed of sound in air. A common experiment to do that. And in order to do this, you would need to work out, if you know the frequency from your signal generator, you need to work out the wavelength. Once you've got frequency and wavelength, you use V equals F lambda. That will give you the speed. However, with standing waves in pipes, the antinode forms slightly outside the open end. So you need to have an end correction. And that's what I've shown here in this diagram. This delta here is representing the extra length on top of the pipe length that needs to be added on to get you from the node to the antinode. So if you were to do this, you'd need to use L1 plus delta is equal to a quarter of the wavelength, because you're going from node to antinode. Then you could use that to work out the wavelength. However, because delta is an unknown, you don't actually know what it is. You need to generate another standing wave so that you can eliminate it from your equations. What you can do is increase the length of the pipe whilst maintaining that same frequency until you can get 3/4 of the wavelength formed in there. So you go a bit longer. I'm not drawing this to scale. And then you'll get, you have a node, antinode, antinode. So you get, that's not drawn well enough. Get something like this. Now, if you assume that the two end corrections are the same, which they will be roughly, then this new length is L2. So you get L2 plus delta is equal to lambda, 3 lambda over 4, because you've got 3/4 of the wavelength there. That's the end of the pipe there. And you can then, because L1 and L2 are known to you, you can eliminate delta from that equation, and that will enable you to determine the wavelength by eliminating that end correction. So that's what we can do for dealing with standing waves in closed pipes. That's the first thing. The second thing is the phase relationship between adjacent points. And here is a standing wave on a string, just to represent, but this applies to all standing waves. I've just marked on there the nodes for that standing wave. And here is a peak. Now all of the points on that section of the standing wave are moving up together. They're actually moving in sync with each other, and down, they'll form the trough together. So they are all in phase. These points here, between these two nodes, they are also in phase. They're forming the trough together, and then they're going up, because that's the when you look at a standing wave, that's the motion you get. It's going up and down. Remember, it's not moving left to right. A progressive wave would be different. You'd see the peak moving across. But between these 2 points here on a standing wave, these are all in phase with each other. So between adjacent nodes, they are in phase. But then the next section, between these two adjacent nodes, all of these are in antiphase to these particles. So these ones are going up whilst these ones are going down. These ones form the peak whilst these ones form the trough, and vice versa. So they are in antiphase with each other, adjacent sections, or you can call them loops. Then if these are in antiphase with each other, these are also in antiphase with each other, but these two sections are in phase with each other, so they're going up and down at the same time. So they're in phase. And that's a note about phase there, which is different to a progressive wave. If I just make it clear, because this peak is moving to the right, these two adjacent points here are out of phase with each other by a certain fraction of the wave cycle. This would be, so if this is 0, this would be 360, this would be 180, 90, 270. So these two here would be 45 degrees out of phase with each other, for example. Because this one is at a peak and it's about to start coming down, this one is already going down. Whereas these ones are all going in sync with each other. And that does mean that this point in the middle that actually forms the peak, that point is moving faster than this point over here, or any of the other points for that matter in that section. Because it's covering a longer distance in the same amount of time. So it's having to move faster. Its average speed would be faster. So that's a note about phase for standing waves. A couple of notes for it.